In this video we're going to look at applications of Newton's second law. Newton's second law states that when an external resultant force is applied to a body, there's an acceleration whose magnitude is proportional to the resultant force and which is in the same direction as the resultant force. Now let's interpret this important statement carefully. Let's interpret it in terms of a very simple example where we've got a small block being pulled across a smooth table by a force P, by a horizontal force P. Since the motion is horizontal, the acceleration must be horizontal, and that means that the resultant force must be horizontal. So the vertical component of the resultant force must be 0. So working vertically, we've got n minus w must equal 0. In other words, n must equal w. The resultant of the system of forces is p horizontally. The size of the acceleration is proportional to the resultant force. So if the pulling force is doubled, the acceleration will double. If the pulling force is trebled, the acceleration is trebled. In general, if F denotes the resultant force acting on the particle of mass m and A denotes the particle's acceleration, then Newton's second law states that A is proportional to F and that A is in the same direction as F. Experiments with a constant resultant force acting on the body, on bodies of different masses, suggest that the acceleration obtained is inversely proportional to the mass m of the body, so that the acceleration is proportional to 1 over m. Putting these two statements together gives us that the acceleration is proportional to F divided by m, or if we like, F divided by m is equal to k times A, where k is a constant of proportionality. The equation F over m equals k times A can be rewritten as F equals k times m times A, where the value of the constant k will depend on the units being used. Now the proper definition of 1 Newton is that 1 Newton is the force required to give a particle of mass 1 kilogram an acceleration of 1 meter per second squared. So F equals 1 when m equals 1 when A equals 1 as well, which means that k must equal 1. So Newton's second law as an equation is F equals mass times acceleration, resultant force equals mass times acceleration. It's important that we remember that F is the resultant of the system of forces, that the equation F equals ma is a vector equation, so the direction of the resultant force and the acceleration are the same, and that we must use SI units when we use the equation F equals m times A. As an immediate consequence of Newton's second law, let's consider a particle of mass m kilograms just after it's been released from rest close to the Earth's surface. The only force acting is the weight of the object, and we know that there's an acceleration of g meters per second squared, where g is approximately 9.8. If we apply Newton's second law now, vertically downwards, then we obtain W, the weight of the object, must equal m times g. So the resultant force downwards is W, the mass times the acceleration is m times g, so we've just shown that the weight of an object is m times by g newtons. So in other words, if we have a body of mass 2 kilograms, then its weight is going to be 2 times 9.8, which is 19.6 newtons. Since Newton's second law is a vector equation, we can apply that equation in any direction. So we can say that the component of the resultant force in any direction is equal to the mass times by the component of the acceleration in that direction. So let's use that to solve 2 or 3 problems. A block of mass 20 kilograms moves across a smooth horizontal surface under the action of 2 constant horizontal forces. The first has magnitude 10 newtons and the second acts in the opposite direction and has magnitude 4 newtons. Find the acceleration of the block and the distance covered by the block as it accelerates from rest to a speed of 1.8 meters per second. Well, we need to start with a diagram. So there's a picture showing our block and the forces acting on the block and the acceleration of the block. If we apply Newton's second law to the right horizontally, we've got the resultant force is 10 minus 4, and that must equal the mass of the block 20 times A. So that gives me 6 equals 20A, so A is 0.3 meters per second squared. I've got a constant acceleration of 0.3 meters per second squared because we're told that the forces are constant and therefore the resultant acceleration is going to be constant. We want to know what the distance of the block, the distance covered by the block as it accelerates from rest to a speed of 1.8 meters per second. We know the acceleration is 0.3, we know the initial velocity is 0, we know the final velocity is 1.8. We're not interested in the time, we want to find the displacement. So we can use the equation v squared equals u squared plus 2ax, which gives me 1.8 squared equals 0 squared plus 2 times 0.3 times x. In other words, 3.24 equals 0.6x, which tells me that the distance travelled by the particle as it accelerates from rest to 1.8 meters per second is 5.4 meters. For our second example, we have a small object A of mass 8 kilograms, which is on a horizontal table, and is connected to another small object B of mass 2 kilograms by means of a light inextensible string which passes over a smooth peg at the edge of the table. Initially the particle A is held at rest and B is hanging freely 1.2 meters above the floor. A is then gently released, and whilst in motion A experiences a frictional force of 4 newtons. We've got to determine the acceleration of A and the tension in the string, the time that elapses before B hits the floor, and determine any additional assumptions that we had to make in obtaining the answers. So we need to put some forces onto our diagram. So first of all, the forces on A, we've got the weight, which is 8g, so that's 8 times 9.8, which is 78.4. We've got the normal reaction, R, perpendicular to the tabletop. We've got the tension in the string and the frictional force opposing the motion of 4 newtons. For the forces acting on B, we've got the weight, which is 2 times g, which is 19.6 newtons, and provided, and since the peg is smooth, we can say that the tension in the string joining A to the peg is going to be the same as the tension in the string joining B to the peg. So, we're also, by drawing the diagram and leaving it at that stage, assuming there is no air resistance. So there's one assumption that we need to make in terms of answering the question. Since the string is inextensible, and we're told that in the question, if A moves a meter towards the peg, then B moves a meter down. If the displacement of A is always the same in magnitude as the displacement of B, then the velocity of A must be the same as the velocity of B, or the magnitude of the velocity of A must be the magnitude of the velocity of B, and the magnitude of the acceleration of A will therefore be the same as the magnitude of the acceleration of B. So we can put the acceleration of A being little a, and that will also be the acceleration of B. Having taken this care over drawing the force diagram and showing the accelerations of each of the two particles, we can now apply Newton's second law. So we'll start off by applying Newton's second law horizontally to A. So the resultant force is T minus F, and that must equal the mass 8 times by A. So we've got T minus 4 must equal 8A. And we can apply Newton's second law vertically to B. The resultant force downwards is WB minus T, and that must equal 2 times A. In other words, we've got 19.6 minus T must equal 2A. So there's my second equation. Now looking at those two equations, we can eliminate T very easily by simply adding the two equations. So if we add equations 1 and 2, we get 15.6 equals 10A, so the acceleration must be 1.56 meters per second squared. Substituting that into equation 1, we will get T is 8A plus 4, so that's 8 times 1.56, add 4, which is 16.48 newtons. To determine the time that elapses before B hits the floor, we know the acceleration of B is 1.56 meters per second. We know that the initial velocity of B is 0. We're not interested in the final velocity of B. We want to find the time, and we know the displacement is 1.2 meters. Now, in saying that the displacement is 1.2 meters, we are in fact assuming that B is a particle, or at least that the lowest part of B is initially 1.2 meters above the floor. Using x equals ut plus a half at squared will then give me 1.2 equals a half times 1.6 times t squared, because the u times t term is just 0 times t, which is 0. So we've got 1.538 is equal to the value of t squared, so t is 1.24 seconds. And we've mentioned the additional assumptions in the course of answering the question, so we've done part C already. At this stage now, there's an example for you to have a look at. So pause the video, have a look at this example, and then when you've done that, we're done.